Hello, scholars. So this week you're supposed to be learning about sampling techniques, which we've talked a lot about. But something that is extremely important to every research study is your sample size. We do not want a sample size in quantitative studies that is too small to infer to the population. So the target population is the group that I would be studying, and a sample is drawn from that population. So if I had a sample, say the target population was all of the adults in the United States, and we're talking 300 million people uh, that we're talking about, maybe they're registered voters or whatever, but maybe I want to study something like that. And I've got this target population of 300 million people. Do you think that I could test a sample size of 20 and gain anything meaningful about a target population of 300 million? No, that sample size would be way too small to give me anything that might be representative of the rest of the population. So sample size is one of the many things that we pay attention to when we sample. And we don't want, it's called a paucity of data. We don't want too little that we can't gain any real meaning from it. Okay, so in statistics, there are a couple of different ways to ensure our sample size is adequate. The first way I'm going to show you is my favorite way and the one I require of my dissertation candidates. It's a free software and a free download, free use called G-Power. It's G asterisk power. And I'm going to share my screen so that you can see what this looks like. Now, the reason I like this so much is because it does other things besides determine what my sample size should be in advance. If you go look at these types of power analysis, I can have my sample size, a priori, a compromise, say I have implied power and a ratio of the power, effect size, sample size. I've got all these things going on. I can do a required, if I know the power and the effect size and the sample size, I can do a post hoc, and I can even just do a sensitivity. How sensitive is my test? So your statistical tests have so much power involved. Okay. We're about to discuss that in a minute. There's more on that in my lectures. Please review all of those lectures. But the first thing we're going to look at is test family type. So in statistics, we have test family types. Okay, look, they're exact tests, F tests, which are ANOVAs and MANOVAs, T tests, which test for group differences by group. Usually it's two groups. T tests are two groups. Chi-square and Z-tests, which I think are mentioned in your lecture this week. Okay, so we're going to do the simplest, the easiest statistical tests are going to be your t-tests because you're either using a mean average score or a median average score, and you're testing for a difference between two groups in mean or median scores. So, and then I have my types of t-tests here. Okay, the most common is the difference between two groups. Mean difference between two independent means or two groups. So that's an independent samples t-test I've just selected right there. And then I want to know a priori how big my sample size needs to be. So I've selected a priori, which is the most common reason I'm going to be in here. So the first thing it asks me is the tails of my test. So I want you to think of that distribution. You know, the bell curve. We had two tails, right? Two ends. We can look to the left, we can look to the right, or we can look at both. Almost always, you're going to be looking both directions. Okay. And I have more of a discussion on that in my lecture, but almost all of you are going to use a two-tailed test. So we'll select that. Now, effect size literally refers to how big of an effect is there. Okay, so usually if you find something, you report an effect size, but I can say I want to pick up on so big of an effect size. So right now I'm going to leave it at 0.5, but if I hover over it, look, small is 0.2, medium is 0.5, large is 0.8. And then the power of my test, which is always 1 minus beta, but the power of the test literally means how powerful is my test to pick up something. In social sciences, we always use either 0.95 or 0.98 or 0.8, excuse me. Medicine uses 0.99. And then look at this alpha error probability. This is in my lecture, but this is the probability of committing a type 1 error. And a type 1 error is a false positive. That's all it means. Social sciences always uses 0.05. Our alpha is always set at 0.05. This is very important for you to know. Medicine will use 0.01. The standard is, so this means that there's a 5% chance of making a type 1 error or a false positive. Okay, so I'm going to always leave my alpha in social sciences at 0.05. My power, I can use 0.95 is the most common. I can also use 0.8. I'll show you the meaning of that in a moment. And then finally, for this test, allocation ratio, N1 and N2. Refers to group sizes. When you're doing a t-test, you want equal group sizes, 50 in this group, 50 in that group. What you don't want are really unequal group sizes because it causes a problem in distribution. So I don't want to do 50 in group 1 and 200 in group 2. Okay, that would be an allocation of 1 to 4. Right, so I want equal group sizes. I'm just going to hit calculate. Now we can see right here my sample size in each group with an effect size of 0.5 and a power of 0.95. My total sample size is 210 with 105 in each group, and it's giving me how powerful my test is. Now, something each of you will have to consider is your access to a sample size. That's a big deal. Maybe you can't reach 210 for your sample size. Maybe you can only do about 100. By the way, for a quantitative study, I don't recommend going below 100 for most of your tests unless you're doing repeated measures. So figure about 100. But let's say you can get 100, but you can't get 110. So watch what happens when I play with these numbers. Say I raise my effect size. So my test can only pick up a big effect, a big difference. I change it to 8. Calculate. Look, my sample size fell. So now instead of 210, I only need a sample size of 84. Okay, or I could put this back to 0.05, what we had to begin with, right? Now, or I can lower the power of my test. Now, don't forget, this is how powerful is my test to pick up a difference or a significance should be, I should say. But what if I lowered the power of my test? Look, my sample size fell again. Okay, now I only need 128. I'm showing you this for a reason. For any of you, access to sample data collection, it's difficult. And I don't care if you're doing quant or qual, and everybody's going to forget to tell you that. Nobody's going to line up to participate in your study. So unless you're using archival data that already exists, you're going to have a very difficult time gathering participants. And many of you are not going to be able to get hundreds or thousands of people for your study. So you need to understand how these numbers can influence to make sure you can actually get to your sample. But look what happens now if I lower my effect size. Say I want it to be able to pick up on a tiny, tiny little difference. Say I want to know if there's a difference in height between boys and girls, and I want to know even if there's just this tiny little difference. I could set my effect size to 1. Look what happens to my sample size. Now I need a sample of 3,142 to pick up on a minuscule little difference, right? And that's at a 0.8 power. Say I set it back to the standard 0.95 power. Look what happens. Now I need 5,200. Okay, so if I want to find a tiny, tiny little difference, that's a small effect size. If I want to weaken my test, I can go with a lower sample size too. Okay, but if I'm only interested in finding a great big difference, I can do a large effect size, and that's a smaller sample. So the smaller the effect size I want to find, the larger my sample has to be. Okay, now look what happens if I change my stuff to a two-tailed test. So with an effect size of 0.8 and a power of 0.95, it's sample size of 84. Looks what happens if I'm only going to look one direction. One direction, one-tailed test. Calculate. My sample size fell again. Now it's only 70. Okay. But looking just one direction makes your test more powerful than looking two directions. So you'd be looking for an increase or a decrease. Usually to the right, it's an increase, and to the left, it's a decrease. And most of the time, you're not going to be ignoring one direction. You're going to be looking for any change or any relationship at all. Okay, so almost never will you be doing a one-tailed test. Please remember that, because that matters on how you write your hypotheses. Okay, now let's say I want to do something a little more simple to calculate my sample size. There's free ones online, which is mentioned in your discussion and your lecture. Okay, so let's look at a couple others because I want to show you some of the important differences here. Okay, so let's look at this one. All right, now do you see this one? This is calculator, sample size calculator from calculator.net. Now, this matters. Okay. Look at this. It says population size. Remember we talked about that target population? So what if I had 300 million, 300,000 million? Okay. And I want a margin of error. We've talked about the margin of error last week, I believe, might have been the week before. They say I only want a small margin of error of 5%. Sometimes we want less than that, but a margin of error of 5%. In social sciences, again, we use 5%. The alpha is set at 0.05. So in social science, that's standard. And my confidence level, 95% is standard. Okay, sometimes it's 97%, sometimes it's less, but 95% would be the standard. I can calculate it. Okay. Now, if I wanted to test all of the adults in the United States, it's telling me how it calculated it and all of that statistical mumbo jumbo, right? And it's saying 385 people. That has to be an example. That can't be right. Hold on a second. Where's the calculation? Oh, yeah, I guess that is right. 385 people for 300 million. That doesn't sound right to me. Does that sound right to you? This is why I don't like these sample size calculators. Okay. And I can also find out my margin of error if I want to provide all of these things. But so a population proportion is the percentage of the value associated with the survey. So it gives this example here. If 33% of Americans have a bachelor's degree, the population proportion for a survey regarding a bachelor's degree should be 33%. Okay, you're not always going to know this answer, by the way, and it's not always even going to be relevant to you. If I want to know what the difference are between boys and girls in the third grade in height, what population proportion comes into play that's affecting us here? We assume that the proportion of boys are 50%, 50-50, right? It could be that the proportion is 51 to 49. Doesn't matter. Okay. That's why it says to use 50% if not sure, because typically we try to go for equal group sizes. Now, there is also another kind of sample size calculator that I was trying to find. One second. Okay, scholars, this other one I mentioned in my lecture. Okay. So many of the free sample size calculators out there, you have to know exactly what kind of statistical test you're going to use in order to be able to use it. There's a big difference between testing for a difference between two groups and testing to see if there's a relationship between two things. Like, does the temperature predict the sale of ice cream cones and hot chocolate? That's a regression, by the way. That's a very different test than the very simple t-test that I keep going back to. Very different, okay? So you can go out there and you can find these free sample size calculators by test. Now notice that it's asking again for stuff more like my G-Power did. Anticipated effect size. How big of an effect are you testing for? Because remember, if I leave it at 0.5, it might not pick up on an effect smaller than 0.5. It might not find a tiny effect. But do you want to report a tiny effect? If there was only a slight difference in height between boys and girls, like an average of 1/4 of an inch at that age, is that even worth reporting? That might be a 0.1 effect size, right? Really small, but is it worth reporting? So if you want to know if an intervention you did, like you tried a new reading intervention to see if you can get reading scores up, okay? And one group of kids got the reading intervention and the other group of kids did not get the reading intervention. If the difference was only a percentage point on a 100% scale, is that worth reporting? Does that have any real meaning? That's why we use effect sizes. Maybe it does. Maybe it doesn't. And then see, remember we talked about desire power level? They use zero 0.8. Remember, 0.95 is probably the most common. And the probability level, this is p-value, which comes from your alpha. Alpha is always 0.05 in social sciences. But I can change all that and I can change my numbers, and it's going to come down here. And look, if I have a minimum total sample size with one-tailed testing, it's 176. If I'm using two-tailed testing, it's 212. All right. Say I do not have equal group sizes. That's what this per group we have equal here, right? So equal group sizes are going to be assumed in these. That's that allocation ratio on G power. Now, seeing the difference between all of these calculators, I hope you can appreciate why I choose G power. I will not require any of you to use G power, but if you are interested in a quantitative study, I urge you to try and use G power. If you need any help with the directions, I have some manuals and things like that on how to use them. They'll make more sense to you after you've completed our statistical class. Like always, I appreciate your attention. Please reach out to me if you have any questions, and I hope to see you at the class Zooms that I'll be holding. Thank you very much.